What element can light up a city or erase it in a flash of terrible light? The answer is uranium, a simple heavy metal forged in the heart of a dying star scattered across the cosmos. It lay hidden in the rocks of our planet, an unnoticed repository of immense power. Then we found it. We learned its secrets. We handed ourselves a wondrous tool and a terrifying weapon. It has changed how we generate energy. It has altered the nature of war. It has redrawn the map of global politics from the strange dance of particles within its unstable heart. For most of human history, uranium was simply part of the Earth's crust, an unremarkable substance locked away in a dark, dense rock called pitchblende. It had no name and no known purpose. Its incredible potential laid dormant, waiting for a species curious enough to find it. That moment arrived in 1789. A year of revolution in France, and a year of quiet discovery in a German laboratory. A chemist named Martin Heinrich Klaproth was analyzing samples of pitchblende from a silver mine. He realized he had isolated a new, unknown element. In keeping with the astronomical discoveries of his time, he named it uranium in honor of the planet Uranus. But for more than a century after its discovery, uranium remained little more than a scientific curiosity. When added to glass, uranium oxide creates a beautiful fluorescent yellow or green color. People handled these objects without a second thought, completely unaware of the strange energy radiating from within them. In 1896, Henri Becquerel found uranium was emitting its own mysterious rays without any external energy source. Marie Curie would later name this phenomenon radioactivity. She and Pierre showed it was a property of the atom itself. To understand the power of uranium, we have to journey deep inside the atom. Think of an atom as a miniature solar system. Visualize the nucleus at the center, protons, neutrons, electrons orbiting. The identity of an element is determined by the number of protons. Uranium is defined by its 92. Its great weight is the key to its instability. This is where radioactivity comes from. An unstable nucleus will eventually seek a more stable state, sometimes by breaking apart. This happens at a predictable rate, a half-life. For common uranium, about 4.5 billion years. Atoms can have different numbers of neutrons, isotopes. U-238 is over 99%. U-235 is about 0.7. U-235 is fissile. A neutron can split its nucleus, releasing energy and more neutrons. A chain reaction. A nuclear power plant is, at its heart, a machine for controlling a chain reaction. It takes the explosive potential of fission and tames it into a slow, steady source of heat to boil water. Natural uranium is enriched to raise the concentration of fissile U-235 from 0.7 to about 3 to 5%. Enriched uranium becomes ceramic pellets stacked into fuel rods, bundled into fuel assemblies. Many assemblies sit inside a large, strong steel vessel, the reactor core. When started, U-235 atoms split, creating a self-sustaining chain reaction. Control rods absorb neutrons to manage fission. A coolant, usually water, carries heat to a steam generator, where a separate loop becomes high-pressure steam, keeping radioactivity contained. Steam spins massive turbine blades connected to a generator, a coil turning in a magnetic field, producing current. Electricity flows out through transmission lines to power cities. Steam condenses back to water and returns to the steam generator. A violent atomic process becomes elegant motion that creates light. While a reactor carefully controls a chain reaction, an atomic bomb is designed to make it happen as fast and as violently as possible. The principle is the same, nuclear fission, but with engineering for maximum destruction. A famous letter from Albert Einstein warned President Roosevelt in 1939. It set in motion the Manhattan Project, one of history's most secret and ambitious undertakings. Across the United States, in hidden cities, tens of thousands raced against time. They had to produce enough fissile material, enriching uranium beyond 90% U-235. Subcritical masses had to be slammed together in an instant, then flooded with neutrons to ignite the chain reaction. On July 16, 1945, the Trinity test proved the theory worked. The unchained fire was real. Less than a month later, this new power was unleashed on Hiroshima and Nagasaki, bringing World War II to an abrupt and horrifying end. The mushroom cloud became an icon of existential threat. Warfare now held the potential for instant annihilation of cities, redrawing global power in a decades-long Cold War. Uranium transformed from scientific marvel to an arbiter of geopolitics. The power of uranium comes from radioactivity, but this same property makes it hazardous. High-energy particles or waves can tear through molecules and damage DNA, the cell's blueprint. A cell may die or misrepair, leading to mutation. Effects depend on dose. A very high short dose, near a blast or severe accident, can overwhelm vital systems. Lower, prolonged doses raise statistical cancer risk over time. Because we cannot see, hear, or feel radiation, it inspires a unique fear, emis and myths. We all receive low levels of natural background radiation. From space, the ground, even our own bodies. Safety relies on time, distance, and shielding. Dense barriers like lead, concrete, or water. Protocols, monitoring, and heavy shielding manage exposure in the nuclear industry. Before uranium can power a city or be forged into a weapon, it must be ripped from the ground, often leaving deep scars. Ore is crushed and leached. The process produces sandy tailings that retain radioactivity from decay chain elements like radium and radon. Without care, wind spreads dust and rain leaches contaminants into groundwater for centuries. The mining legacy hit indigenous communities hard. Poorly ventilated tunnels and radon exposure led to illness and loss. Cleanup is slow and costly. Engineered liners, rock and soil caps to secure waste for millennia. It is a debt owed to the land and to the communities that bore the burden. As we move away from fossil fuels, uranium is again at the center of fierce debate. Nuclear provides reliable, round-the-clock power with minimal carbon. But costs are high, timelines long, and public fear persists. Small modular reactors promise factory-built modules and passive safety to reduce cost and risk. Breeders, high-temperature designs, and waste-burning reactors hint at a different future. But many face decades of development. Spent fuel stays hazardous for millennia. Pools and dry casks are temporary. Deep geological disposal is the leading solution, yet siting remains difficult. We have journeyed from a simple grey rock to the heart of a star on Earth. We have seen how a gentle fire can light a city, or a terrible storm can destroy one. Uranium itself is neither good nor evil, it simply is. The morality enters the picture with us. Our history makes triumphs and failures. Climate change now rivals nuclear war as an existential test of our choices. Uranium can power our future or destroy it. So will humanity finally learn how to control the most powerful element it has ever touched?